Let us look at cosets of a subgroup. Cosets are subsets of a group formed by applying the group operation between a fixed group element and all elements of a subgroup. Okay? So let's say we have a group G and a subgroup H of G. Now H is in G. We know that since it's a subgroup. It forms cosets of two types, left coset and right coset. So left coset is formed by A times H, where H is in the subgroup H and A is in group G. So here, remember, between a fixed group element, here A is the fixed group element which is being multiplied by H, which is an element of the subgroup H. So A times H, where H is in H, A is in G, and this we normally write it as A times capital H. So the difference between the small h and the big H is that this small h basically tells us that we are talking of a particular element of the subgroup H. What we are doing is we are taking all elements of a subgroup and multiplying them one by one with A. So because we are doing that, we write it as A times H, capital H, that is subgroup H. So this means take an element A from the group, multiplying it with each element of the subgroup. Similarly, we have a right coset, which is H times A, where H is in H and A is in G. And we generally write it as subgroup H times A. So here, how does left coset name come? Because the group element is on the left. And here it is right coset because the group element comes on the right. So which means when you finally write the cosets, you should make sure that the appropriate, or rather the group element is on the appropriate side of the subgroup element. Okay. Now here, H is the coset of itself, since E times H, E being the group element, and when we multiply it with each element of the subgroup, the element of the subgroup does not change. So which means to generate cosets other than H, because H we already have as a subgroup, and is a coset of itself. So if you want to generate cosets other than H, we must take only A times H or H times A, where A is in G backslash H. What this means is that A is in G, but not in H. Let's take an example and work on it. Let's take the group Z4, that is integers addition modulo 4 group. Now we take a proper subgroup of G, that is H will be the subgroup generated by the element 2 in G. So here 2 is the generator which will generate 0, 2. Now we start off with a table. So let me explain this table. A is an element from G. G contains what? Since it is Z4, it will contain 0, 1, 2, 3. Now, to generate the left cosets, we take an element from G, and in this group's case, the group operation is addition modulo 4. So we add. So plus H. We do this for each element from the subgroup H to get the left coset. Similarly, we reverse the order to get the right coset. So let's take it one by one. So 0, 1, 2, 3 are the group elements. And the subgroup elements are 0, 2. So 0 plus 0, 0 plus 2, which gives us 0, 2. Then 1 plus 0, 1 plus 2, which gives us 1, 3. 2 plus 0, 2 plus 2, which gives us 2 plus 0 is 2, and 2 plus 2, remember, it is not 4, it is 0 under addition modulo 4. Next, 3 plus 0, 3 plus 2. So 3 plus 0 is 3, 3 plus 2 is 1. Okay, so we have got the left cosets. Now we repeat the same exercise. The only thing is we take the group element on the right. So we have 0 plus 0, 2 plus 0. Then we have 0 plus 1 and 2 plus 1. Then we have 0 plus 2, 2 plus 2. Then we have 0 plus 3 and 2 plus 3. And now we add it up, we get 0, 2, 1, 3, 2, 0 and 3, 1. So we have got the right cosets. Here we could have reduced the number of rows by not including the elements of H. So we didn't follow this rule that A should be in G backslash H. That means A in G but not in H. So that is the advantage of following this rule. It reduces our effort. Just wanted to give you an idea of that. That is why I did it fully. Now here, remember, Z4 is an abelian group. That means the addition is commutative. And since it is abelian, it means it doesn't matter in which order you add. So that means the left coset and the right coset will be the same. The distinct left and right cosets are, now here remember there might be duplicates in the right and left cosets. There's no point in repeating them. So we say distinct left and right cosets are 0, 2 and 1, 3. So since Z4 is abelian, A plus H equal to H plus A, and hence left and right cosets are the same. Now let's take another example, which is non-abelian. So now let's take cosets of symmetries of equilateral triangle. Remember S3, rotation, reflection. So let me just present it to you very briefly. So we have seen this, cosets of symmetries of equilateral triangle. Here E is a rotation of 0 degree, R is a rotation of 120 degree. This is applying R twice, so which means rotation by 240 degrees. This is flipping it across a line of symmetry. R times S is another reflection symmetry, and R square times S is another reflection. The group contains these actions: E, R, R square, S, S times R, and S times R square. Now we take a proper subgroup H, let's say generated by R. So we have E, R, R square. Now, because we are going to do multiplication and all that in this case, so let's put some standard ones. So R cube, remember rotation by 120 degree is R. So we apply it 3 times. So which means we come back to 0, which is nothing but E. S square, if we do a flipping across a line of symmetry twice, we come back to the original position. S times R is equal to R square times S. R times S is equal to S times R square. Here remember the order. Be careful about this. S times R is R square times S, and R times S is S times R square. Remember, to generate cosets other than H, we must take only those elements from the group which are not in H. So here, those elements which are there in G but not in H are, H contains E R square. So except these, we take up the remaining S, comma, S times R, comma, S times R square. And we have the subgroup E R square. I'm just repeating it here so that we can do the multiplication here itself. So now S times H, we are going to look at left cosets. S times capital H means what? We take an element from G slash H and multiply it with each of these. So S times E is S. S times R is S times R. S times R square is S times R square. Now S times R, the second element from G slash H, multiplying with each of these. So S times R times E gives us S times R itself. S times R gives us S times R square. Then S times R square gives us S times R cube. R cube is E. So S times E is S. Now the third element, S times R square times elements from H. So we have S times R square times E, that is S times R square itself. S times R square times R is S times R cube, which is S, because R cube is E. And finally, S times R square is S times R to the power of 4, which means S times R, because R to the power of 4 is R itself. Okay, so all of the above left cosets are the same. So here also we have S times R and S times R square. Here also the same, and here also the same. So there are two distinct left cosets. The subgroup itself, E R square, and we can take just one of them and say S times H is equal to S times R square is the left coset. Now let's find the right cosets. H elements from the subgroup and the first element from the group. So that is H times S, which is E times S, which is S itself, R times S, and R square times S. This was pretty straightforward. Now let's look at the second one. So here H times S times R. So let's take it forward. We have E times S times R, which is S times R times S times R, and R square times S times R. Now here we need to do simplification. S times R as it is. Now R times S times R. Take it right to left. S times R is R square times S. So we have R times R square times S, which gives us R cube times S. Okay. Now here R square times S times R. So again, S times R is R square times S. So R square times S, which is R to the power of 4 times S. Okay, we can simplify it further. So we have S times R cube is E, identity. So S. R to the power of 4 is R. So R times S. Here, since this is a right coset, make sure that the elements from the group are on the right and the elements of H are on the left. So here we have S times R. Here the group element is on the left. So S times R is R square times S. So write R square times S. S as it is and R times as it is. So this is the right way of writing the coset. Okay. Now let's look at the third element. H times S times R square. So we have E times S times R square, R times S times R square, R square times S times R square. Now simplifying this, E times S times R square is nothing but S times R square. Now R times S times R square, how do we simplify this? Take it again right to left. S times R square is R times S. So we have R times S, which is R square times S. Now R square times S times R square. So here S times R square is R times S. So we have R square times R times S, which is R cube times S. Now again, make sure that it is written properly. So S times R square, the G slash H element is on the left. It should be on the right. So S times R square is R times S. R square times S and R cube is E. So S. Again, you will notice that all the above cosets, right cosets, are the same. So there are two distinct right cosets. That is the subgroup itself and H times S. We can take any one of these. Simplest one is this. So H times S. Similarly, we can choose any other subgroup and find the cosets. Remember, cosets partition the groups into disjoint subsets of equal size. So here look at the cosets. They are of equal size. Here you have three elements. Here also you have three elements. And none of the elements that are there here are there here. And none of the elements that are here are there here. So they are disjoint subsets of equal size, which basically means that the cosets partition the group because the group contained 6 elements and these two are disjoint subsets of that group. So that was cosets of a subgroup. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.